This quiz focuses on understanding how SparseRandomProjection, a dimensionality reduction technique in scikit-learn, works, especially with sparse data. We'll explore its efficiency, key parameters, and limitations. Get ready to test your knowledge. This question asks you to evaluate several statements regarding the practical application of SparseRandomProjection in a specific data context, a large sparse dataset. You'll need to know its features and limitations to answer correctly. I find this statement true. SparseRandomProjection is designed for sparse data. It cleverly skips calculations on zero entries, making it much faster than GAUSSIANRANDOMPROJECTION, which doesn't have this optimization. This is also true. The density parameter controls how many non-zero elements are in the projection matrix. A lower density means fewer computations, resulting in speed. However, too low a density can lead to information loss, decreasing the quality of dimensionality reduction. Think of it like compressing an image, faster, but potentially lower quality. I agree, this is true. The random_state parameter acts like a seed for a random number generator. Setting it makes sure you always get the same projection matrix, allowing you to reproduce results reliably. It's important for ensuring consistent experiments. This statement is false. SparseRandomProjection doesn't automatically handle missing values, nans. You must pre-process your data, for example, by filling in or removing those missing values, before using SparseRandomProjection. I found statement D to be false because sparse random projection doesn't automatically handle missing values, nans. You need to pre-process your data. First, either fill in the missing values or remove rows, columns containing them. Think of it like this. Sparse random projection is a tool that works on numbers. It doesn't know what to do with missing information. I determined statements A, B, and C to be correct. Sparse random projection is super efficient for sparse data. A. The density setting affects speed and accuracy. B. And using _random_state_ makes your results repeatable. C. These statements accurately reflect how sparse random projection works. I'm explaining sparse random projection, a scikit-learn tool for dimensionality reduction. It's especially useful when you're working with large datasets that have mostly zeros, what we call sparse data. Think of it as a smart way to shrink your data without losing too much important information. We'll explore how it works and why it's better than other methods for sparse datasets. This is a multiple-choice quiz, testing your understanding of sparse random projection. We'll look at several statements about it and decide which ones are true. This question is asking you to evaluate several statements about how sparse random projection works and its properties. This question focuses on understanding which claims about sparse random projection are factually correct. This statement is true. I'll explain why. Sparse random projection is designed to work efficiently with sparse matrices filled with many zeros. It skips over these zeros, unlike Gaussian random projection which processes every element. This speed boost is significant when working with huge sparse datasets. This is also true. The density parameter controls how many non-zero elements are in the random projection matrix that sparse random projection creates. A lower density means fewer computations, which is faster. However, reducing the density too much can lead to information loss and reduced accuracy in the dimensionality reduction. Correct again. The random_state parameter acts as a seed for the random number generator. If you set it to a specific value, you'll get the exact same projection matrix every time you run sparse random projection. This is essential for reproducibility and allows others to replicate your results. This is false. Sparse random projection can't handle missing values directly. You must pre-process your data, e.g., by filling in missing values or removing rows, columns with missing data, before using it. This quiz tests your knowledge of the SparseRandomProjection tool in SCIKITLEARN, a popular Python library for machine learning. We'll explore its efficiency, key parameters, and limitations when working with sparse data that mostly contains zeros. Let's dive in. I agree. SparseRandomProjection uses the fact that the data is sparse to speed up calculations. It cleverly avoids unnecessary calculations for the many zero entries, making it much quicker than other methods like GAUSSIANRANDOMPROJECTION when dealing with sparse datasets. I think this is right. The DENSITY parameter controls how many non-zero elements are in the projection matrix. Setting it low speeds up computation because there's less work to do. However, making it too low can throw away too much information, hurting the accuracy of the dimensionality reduction. It's like trying to summarize a long book. You can do it quickly with a short summary, but you might lose important details. I agree, this is spot on. The RANDOMSTATE acts like a seed for the random number generator, ensuring that if you run the code multiple times, you'll get the same results each time. That's crucial for reproducibility and making sure our experiments are consistent and reliable. I disagree. SparseRandomProjection can't handle missing data, NaNs, on its own. You must pre-process your data, perhaps filling in the missing values or removing rows with NaNs, before using it. Think of it like trying to build something with missing parts. You need to fix those before you can put it together. This statement explores the trade-off between speed and accuracy when adjusting the density. A lower density means fewer computations but could lead to a loss of information, and hence a less accurate outcome. This statement focuses on the tool's ability to deal with missing data, which is important for data cleaning and preparation for the SparseRandomProjection process. This is important for the robustness of the model that will be built. This statement discusses the efficiency comparison between SparseRandomProjection and another dimensionality reduction method, GAUSSIANRANDOMPROJECTION, when both are used on sparse data. This is relevant because the choice of algorithm can impact runtime significantly depending on data characteristics. This statement highlights the importance of the parameter RANDOMSTATE for the reproducibility of results. This is crucial for validating results across experiments and for debugging any issues. Reproducibility is a core principle for scientific results. This question introduces the core concept of the quiz. This establishes the context for the following statements and is crucial for understanding the entire exercise. I found that statement A is true. Sparse random projection is specifically designed to work well with sparse data, meaning data with lots of zeros. It's smarter than GAUSSIANRANDOMPROJECTION because it takes advantage of those zeros, avoiding unnecessary calculations and thus boosting its speed. Statement B is also true. The DENSITY parameter controls how many non-zero values are in the projection matrix. A smaller DENSITY means fewer calculations, making it faster, but it could lose some information which leads to a slight reduction in accuracy. Think of it like using a lower resolution image. It's faster to process, but you lose some detail. I discovered statement C is true. RANDOMSTATE acts like a seed for the random number generator. Setting it ensures you get the same random projection matrix every time you run your code. This is essential for getting consistent and repeatable results. Without it, you might get slightly different projections each time, even with the same data. I found that statement D is false. SparseRandomProjection doesn't automatically handle missing values. You need to deal with NaNs, not a number, before using it, for example by filling them in with estimated values or removing rows, columns with them. I'm focusing on understanding how scikit-learn's sparse random projection works, especially with large, sparse datasets. It's a crucial dimensionality reduction technique. This question tests my knowledge of sparse random projection. I need to carefully evaluate each statement to determine its accuracy. This statement says that sparse random projection is faster than Gaussian random projection for sparse data. This is true because sparse random projection takes advantage of the many zeros in sparse data. Lower density means fewer non-zero entries in the projection matrix. This makes the computation faster, but could lead to some information loss and reduced accuracy. The random_state parameter acts like a seed for the random number generator. By setting it, I ensure I get the same projection matrix each time I run the code. This is crucial for reproducibility of experiments. This statement is incorrect. Sparse random projection doesn't automatically handle missing values. I have to pre-process the data, e.g., by imputation or removal of missing values, before using sparse random projection. I'm working with a sparse dataset, meaning it has many zero values. It's in CSR, compressed sparse row, matrix format, a common efficient way to store sparse data. This is the specific algorithm I'm using to reduce the dimensionality of my sparse dataset. My goal is to get a lower dimensional representation of my dataset after applying sparse random projection. This is a quiz focusing on understanding how SparseRandomProjection in the scikit-learn library works. We'll examine its efficiency, parameter effects and limitations, particularly when handling sparse data. Let's dive in. This question challenges you to identify accurate claims about SparseRandomProjection, a dimensionality reduction technique in scikit-learn that's particularly useful for large sparse datasets. We'll evaluate each statement against our knowledge of this technique. The DENSITY parameter controls how many non-zero elements are in the random projection matrix. A lower DENSITY means fewer calculations, leading to faster processing. However, too low a DENSITY might lose important information, making the dimensionality reduction less accurate. It's a trade-off between speed and precision. Think of it like this: if you're summarizing a long story, you want to keep the most important parts, but if you leave out too much detail, you sacrifice accuracy. The RANDOMSTATE parameter acts like a seed for the random number generator. By setting it, I guarantee that the same random projection matrix is created every time, ensuring consistent results across multiple runs. This is crucial for reliable experiments and comparisons. This statement is incorrect. SparseRandomProjection doesn't automatically handle missing values, represented as NaN. You must pre-process the data to deal with them before using the technique. Think of it like trying to build a house with missing bricks. You can't build a whole house without them. Similarly, SparseRandomProjection needs complete data to function properly. SparseRandomProjection is designed specifically for sparse data, meaning it has a lot of zeros. It takes advantage of this sparsity by only performing calculations on the non-zero elements. In contrast, GAUSSIANRANDOMPROJECTION doesn't do this, wasting time on many unnecessary calculations of zero-valued elements. This makes SparseRandomProjection substantially faster for such data. Our data is a CSRMATRIX, compressed sparse row matrix, which is a way to efficiently store sparse data in computer memory. This means the data has many more zero values than non-zero ones. This is the scikit-learn algorithm we will use for dimensionality reduction. This algorithm is optimized for speed when dealing with sparse data like ours. After applying SparseRandomProjection, we'll have a new dataset with fewer features, dimensions, but hopefully still representing most of the important information from the original dataset.